In general, namely, one of the students asked me that he is doing some model in his master's thesis. He's describing and explaining something by means of a model, and then the question is that this applies somehow, or the other way around, I've got to tell it, somehow paradigm theory applies to that sort of research because it's a part of normal science. Many people use this sort of model, so it's a part of it, and there's a consensus about it. So it seems to be a part of normal science. And on the other hand, also systematicity theory has something to say about it, namely that here modeling is something for the explanation. So isn't there a tension, or isn't there a difficulty? The answer is no, there's no difficulty whatsoever, because there are sometimes paradigm theory and systematicity theory can explain something. And also if you have, for instance, explanations according to this model that deductivism presented, that is, of course, fine, and this may also be a part of normal science, these sort of explanations. And also systematicity theory has something to say about it, namely it's a more systematic way of explanation than in everyday life. So it is quite possible that your research is then covered by three of these theories, right? This is not exclusive. I mean, all the later theories always want to learn something from the earlier theories, correct their shortcomings. But that doesn't, of course, exclude that there is a substantial overlap between the different philosophies here. So don't worry if your result is, well, I can describe what I do both by, say, deductivism and by paradigm theory and also by systematicity theory. It's no contradiction. That's fine, right? It may be that you say, no, what I'm doing is really only captured by whatever it is then, right? Inductivism or whatever it is. So don't worry about that when you go through these different disciplines. Then you'll discover that, right? This applies, or that doesn't apply, or both apply, or none applies, whatever it is, right? Remember, the idea of the exercise is that you both think about the theories and you think about your work, right? And the result then, we'll see, we'll discuss, we'll find out, right? And it may be interesting, or may say, well, yeah, I didn't learn very much by it, but I connected at least these things. And that seems to be what is good for your education, okay? So don't worry about that. I can't predict the results, how you apply that. There are very different results. I've seen that during the last 12 years, when the students connected the philosophy of science with their work. They're very different results, just depends on what you're doing. What you will see then, when you hear during the next two sessions, how different the sciences are and how different the research projects are. And that's then, of course, reflected how differently the philosophies of science can be applied to them, right? So don't worry about strange results. We'll see, we'll discuss it. So far, every of the students has survived it, right? Which is a cause for optimism, right? Nobody committed suicide afterward or was killed during the presentation, right? Nobody did. And apparently students are comparatively happy with what they learned during this exercise, all right? Any other questions because of the upcoming presentations? When we start next week, you remember that. I cannot tell you the name right now, but I put the list on the internet, so the first 6 who start next week. So everything okay with you? I gave you explanations last time, simply we start, okay? Don't worry about it. All right, so we come to the next of these 9 dimensions, the defense of knowledge claims, which is, of course, concerning the activities of science, also of extremely vital importance, because the reason is very simple, because we know that knowledge claims can be false, they are fallible, they are subject to error, to mistakes, and we can be wrong. And as science is an enterprise, both, of course, engineering science and the other sciences as well, is an enterprise in which we want to have solid knowledge, right? Good knowledge, true knowledge in the very best case. We must be careful that we don't err. And therefore, we have in science a systematic attempt at error elimination. We also in everyday life try to eliminate errors, right? If you think you can go to whatever it is, you can go to the Mensa and you start going out here and then turn to the right, then you are erring. And someone will tell you, look, did you want to go to the Mensa? No, you have to turn left don't go right here, right? We may be wrong, and then somebody corrects us, or you look at the map and say, oh, damn it, I thought I have to go right. No, I have to go wrong. I have to go left. This is wonderful. We do the same. But the point is that in science, we do that much more systematically. Right? This is, again, the same story again and again in systematicity theory. We have the same sort of situation. We know that we can make mistakes. We can err. We can go wrong in thousands of ways. But the difference then between everyday life and science is that we try to eliminate these errors in science much more systematically than we do in everyday life. And I give you a few examples here. Again, this could fill hours and hours and hours by going through different sciences. So if you go to the formal sciences, mathematics, of course, being the main candidate here, mathematics, of course, you eliminate possible errors by giving a proof, right? And a proof is something that establishes the truth of a theorem relative to axioms in a way that is unshakable. That's the idea of a proof. Proof establishes certainty, right? That's the idea. Unfortunately, we only get that in mathematics, right? We don't get that in the natural sciences and in the other fields of science, but we get it in mathematics, but only there. And that's, of course, the hardest way and most systematic way of eliminating any sort of error by proof. In the non-formal sciences, empirical sciences, one might say, of course, empirical data play a preeminent role. As you know, or I think all of you in your master's thesis, of course, you have to deal with some sort of empirical data that you generate or you collect or whatever you do. And then it is strongly domain dependent what procedures you are using in order to make use of the empirical data in order to defend knowledge claims. Right? That depends very much on the area you're working with. When you work in economic history, you make very different use of empirical data than, say, in plant biotechnology. When you use empirical data in order to improve your design or think about your design and make specifications of your design when you build a dam, for instance, of course you make very, very different use of the empirical data than in other disciplines, again. So it's extremely domain dependent what we do with the data, experiments, criticism of sources. And of course, the use of data is in particularly important when it comes to theories, to these general theories, because general theories are speculative in principle. Right? They talk about things you cannot observe. If you look at quantum mechanics, for instance, about which you, I guess, don't know very much, but quantum mechanics speaks about a wave function. Traditional quantum mechanics speaks about a wave function, but you cannot observe this wave function. It's unobservable, right? You cannot observe it. Simply, in principle, you cannot observe it, right? Also, if you speak about a field theory, you cannot directly observe these fields. They are theoretical entities. They are postulated by the theory. And of course, you can postulate whatever you want, right? But you've got to postulate the right things that hopefully really exist. And then you must, of course, test these theories as strongly as possible because, as I said, they're speculative, and that means you don't know whether they are right. And therefore, you must test them in order to eliminate the bad ones, and then you hope you stay with the good ones. And that must be, of course, done extremely systematically. Theories are risky. They are extremely rewarding. I told you about theories, their unifying force, their power to unify explanations and give you very strong explanations. That's wonderful. Therefore, of course, in the theoretical sciences, people love theories. In biology, think of evolutionary theory. It's an extremely interesting theory, but it's, of course, speculative in the sense that you cannot directly observe it. Right? You can only say, okay, here I have a phenomenon, I can explain it by means of roughly speaking, mutation and selection, but you cannot directly observe mutation and selection in this general way as the theory of evolution postulates these processes and their effects on the diversity of life and the development of life forms. So we have to test them, and this is, of course, a huge thing, of course, testing evolutionary theory or quantum mechanics or gravitation or whatever it is. So this is absolutely essential, and of course it's done much more systematically by systematic experiments and so on to test these theories. In the historical disciplines, there are also procedures, systematic procedures with respect to sources. So when I give you an explanation of why this street did this turn here, then I can't observe this castle here any longer. Then I got to go to certain sources, written documents, right? And I must then find documents in which is documented that there was indeed this castle here, and I must find the document that indeed the owner of the castle did have good relationships to the king. And then, of course, you know that some of these documents are falsified for some reasons, right? And you've got to be critical about that. And that is what is here called systematic procedures with respect to sources, because in the historical disciplines you must always be extremely careful that your sources are truthful. They are just false documents. You know, they sit around. For some reason, someone has falsified a document, and a historian, you must find out whether the document you rely on is a truthful document or whether it's a falsification. And that's something highly, highly developed. Of course, we do the same in everyday life. Of course, yeah, there are falsified documents and falsified signatures and whatnot. And of course, we have our standard procedures how we do it. In everyday life. I mean, every banknote you get may be a falsified banknote. And if you look at the supermarket, what people do, then they look, for instance, at a UV ultraviolet light, and you see it, there are certain marks on the banknotes that we can distinguish that. And we do that, you know, it takes us 5 seconds or something, or usually you don't do it at all. You simply trust that the money you get is real money. If you compare these everyday practices, then of avoiding error, then what you see immediately that in huge errors it's just less systematic than what we do in the sciences. Again, here you find the general thesis. And here's another aspect that's important of quantification. Why is it that the sciences love mathematics? All the sciences, more or less, or at least apply mathematics. I gave you already in the section on descriptions an argument. Descriptions become more systematic when they are quantitative. But also with the recourse defense of knowledge claims, the quantitative form of knowledge claims is very, very important for their possible justification. I just read in a book about the prehistory of plate tectonics, right? The idea that the continents on the Earth sit on plates and these plates are moving. This is an idea that was not introduced, but this was accepted in science in the 1970s, but it has a very interesting prehistory because the idea already came up in the very early 20th century, but was not accepted. And one of the things that was important there, that people had certain ideas in geology about how it comes that the mountains were formed and that we have certain regularities on the Earth. But as long as you talk there qualitatively, you could not justify certain statements or refute certain statements. And only once you quantified certain statements, for instance, about energy flows, right? Energy flow is something extremely important in geology, of course, because the interior of the Earth is hot. Its radioactivity was very important for geology, the discovery of radioactivity, because that changed all the judgments of the age of the universe and of the Earth primarily, and then of the universe, of course. So it was very important to have quantitative statements there, because with quantitative statements you can refute certain ideas that are qualitatively quite plausible, right? You may say, and this was one of the ideas, you may say that, and as I said, in American geology, this is one of the ideas, that the mountains are the result of the shrinking of the Earth, right? Like the shrinking of an old apple, and then the polished surface becomes gets little mountains, right? And the idea was this could be the main reason why we have mountains on Earth, because the temperature of the Earth decreases, and therefore the Earth shrinks, and that, of course, on the surface builds mountains, which is quite a plausible idea, basically. But then people simply calculated, right, quantitatively, what the maximum effect of the shrinking is, because you know what the temperature differences are, and then you could calculate what the maximum effect of the shrinking is, and whether that could account for the highest mountains on Earth, and the result was negative, right? So by using mathematics here, you could refute a certain qualitatively very, very plausible idea, which was a mistake. Well, which was not a mistake, it was an error, it was just false. And by having this idea in quantitative form, then you could refute it. You could just calculate what the maximum effect was under certain assumptions, what the maximum effect was of the shrinking of the Earth due to the temperature decrease on the surface, right? And then the effect was that is much, much, much lower than 10,000 meters, 9,500 meters of the Mount Everest, right? So you couldn't explain it, and then people knew it. The theory that the surface of the Earth is primarily a result of the shrinking Earth is false, and one needs a different theory, right? So this is a very interesting case, I think, and it's very typical of many situations, and why the sciences, the natural sciences, but also increasingly, also now the humanities and the social sciences, why it is extremely desirable to have quantitative statements, because then you can make the error, the defense of knowledge claims and the error elimination much more effective. Where on a qualitative level, you say, yes, that's a plausible theory. I mean, it really looks like a shrunken apple, right? The Earth. So that could be right. But then by quantitative considerations, you can show, no, it's wrong. You must go for another explanation. So this is, of course, again, if you look at that, our everyday explanations are, of course, our everyday knowledge claim defense is, of course, very, well, mostly of a qualitative character. Of course, it's qualitative. And of course, as soon as you have quantified parts of science, you see immediately why this systematicity theory about defensive knowledge claims is right. It's more systematic by using just mathematics. So everything that is quantitative in science and successful, one has to add, is then by the quantitative character, of course, more systematic than almost all of what we do in everyday life and in other areas of knowledge, right? So you get the plausibility of systematicity thesis here again. All right. So let's go to the next one. Is that plausible? I guess it is. Yes. If not, please come back to me. Now here's another interesting thing. It's called critical discourse, and that's an aspect, that's a social aspect of science, right? It concerns the social organization of science. How people interact in science, right? That's not about scientific knowledge, but about the social organization of science. And that's something you are also already, because you've been long enough now, students in different areas, that is something you see immediately and are familiar with, that critical discourse is necessary as scientists commit mistakes or are wrong for other reasons. And critical discourse is people interacting, talking to each other mainly, in order to avoid mistakes. You know, what the critical defense of knowledge claims, or the defense of knowledge claims, sorry, section 4, is implemented or realized by real human beings who talk to each other, right? Like we talk here in class, or I talk most of the time because you don't say anything, you don't want to talk to me. All right, so critical discourse is something which you find here, and we find many social institutions in science that systematically establish critical discourse. And the idea of critical discourse, again, is to find out weak points, right? Mistakes, errors, wrong assumptions, and so on and so forth, and people talk to each other. And this is, we also do that in our everyday life. We talk about things, right? And critically, and say, you think, oh yes, Hans and Hannah will be a dream couple, and you know, they have the same whatever. Look so similar and like both the opera and hate football and whatever, and then we talk about that, and someone else said, well, that's unimportant whether they both like football. There are other couples where one likes football and the other one not. Typically the woman loves football and the man finds it disgusting because he rather talks to his colleagues or whatever. Anyway, so we know that this critically talking about assumptions and stuff is something of everyday life, but it's much more systematic. There are many social institutions in science that systematically establish this critical discourse. And here I give you just a few examples. Peer review system for publications. You know, when you write up a publication, you send it to a journal, then there will be peer review, and that means 2 people, depending on the area where we work with, between 2 and 5 people or so, then read your paper, write a report on it, give it to the editor, and tell him whether your paper should be accepted without revisions, whether you should do revisions on the paper, or whether the paper should be refuted. Okay? So if you send a paper to Nature, the chance that the paper will be accepted is very low, something like 5% maximum, right? 95% of the papers in Nature are refuted. Not good enough. So this is the peer review system, and that's of course a social institution, right? That is how people interact. When you send a paper to a journal, then there are other people who do this and that's systematically done in order to refute, to reject the bad papers and get the good papers. So if you read scientific journals, there are sometimes discussion sections, right, where someone will reply, so you have even full discussion sections where people reply to other papers, right, where they were criticized or lauded or whatever, and then they reply. So there's an institution of discussion. Where there are critical review articles, right, where you have, it's also existent in almost all fields of science, well, not everywhere really, but very often, of course, in the more theoretical sciences, where you have a review article that reviews what happened in the last 10 years. And then there may be some 1,000 articles summarized somehow, and the whole story is told, and when you read these articles, then you know, of course, what's going on and what was important, was less important, and that's, of course, also a critical consideration of what was going on. You have book reviews, also in the journals. You always have book reviews. If you look at Nature, there's a book review section in which important books are reviewed and criticized, right? And said, yes, this book is good in that respect, bad in that respect, uninteresting, blah, 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 missing this and that. Then you have, in scientific talks, you have always a discussion period afterwards, always, apart from the talks for festival reasons or so. So you will experience that in 1 week from now, right? After each of this talk, there will be a critical discussion, right? That's a social institution, you know, it's part of the game. It's like when you start talking to someone, you say hello first, right? Or introduce yourself. And therefore, this is also a social institution of science. Whenever you have scientific talks, they are followed by a discussion. You have conferences in which people talk all the time, right? Be it lectures and then discussion periods, or people meeting everywhere, and that's the main function of conferences, that you talk to each other and listen what the others have to say and criticize each other. The social organization in big science is also interesting. I'm not going into detail. I'm just telling you what the story here is. If you go now to Geneva to the Large Hadron Collider, you know, this new accelerator that's there, the first paper that was published there had 1,500 authors. 1,500 authors. So in this is big science, right? You have 1,500 physicists collaborating in one single experiment, right? And of course you must organize, and this is an absolutely non-trivial task, how you get 1,500 people together in one experiment and an organization such they can share whatever their specialty is. And they come from 60 or 80 different institutions all over the world. That is how big science is organized today, right? You have up to several thousand people working there from many parts of the world, from many dozens of institutions, 60, 80 institutions. And of course, somehow you must organize that you get from every single member of this group, you've got to get the right information. And that's, of course, a major task. And it's absolutely fascinating what is happening here during the last 10 years or so. I mean, 10 years or so, well, 20 years or so ago, the maximum was something like 100 people working in a group, right, in one experiment. And now you have, if you look at these papers, you have 7 pages in the beginning of the paper just listing the name of these 1,500 people and their institutions. I mean, this is gigantic. And of course, you have to find institutions, and they are well established. There are sociologists now studying these social institutions of big science. It's extremely fascinating because the scientists have to be creative and innovative, not only with respect to their apparatus, where they have to be extremely creative and innovative, but also in organizing themselves. Right? That's very strange, but that's also part of science. Okay, I got to continue a little faster now. Here's something else which is important of science and also very systematic. It's called epistemic connectedness. I cannot tell you extremely much about epistemic connectedness on an abstract level because it cannot be very precise on an abstract level. I say just it means all sorts of logical and relations like logical dependency or confirmation or generalization or citation. Don't worry about that too much. What the relations mean depends on context, but I tell you what the purpose is of that. Why does systematicity theory talk about epistemic connectedness? The basic idea is that it's one of these features of scientific knowledge in comparison to other forms of knowledge, that the knowledge is fairly well connected among each other, right? Different pieces of knowledge are very well connected and strongly connected with each other. So, for instance, if you want to distinguish, I talked about that already once, I think shortly, if you want to distinguish product development from applied research, for instance, automobile engines, or in chocolate research, which you are not familiar with, but there is a research area, the science of chocolate, right? The designing and making of chocolate. There's a scientific engineering discipline, or in automobile engines. There is a difference between the following two activities. What the engineering departments in technical universities do concerning automobile engines, when they, for instance, study the process of the burning of the fuel in the cylinder, right? What's exactly happening there? That's on a very general level. When you compare that with what happened in an automobile factory where engineers improve a certain product, right? For the next model, they put in the same engine, but somewhat improved. That is something that doesn't count as engineering science. This is product development, right? That's not engineering science. So what's the difference between this product development on the one hand and what happens in these more general engineering science disciplines? The difference is that the scientific side is just knowledge that's much more epistemically connected, meaning in this particular case, many, many more applications. So what you learn in your university studies at a technical university in engineering science is something that you can apply on many, many different occasions, right? So it's got many connections to particular cases. Whereas what you do in product development, you develop a particular product. And the knowledge applies then to this particular product only. And it's only very rarely that you can apply exactly the same knowledge in other areas. So the difference between engineering science knowledge and product development knowledge is that the engineering science knowledge is much more epistemically connected. Epistemically means knowledge, right? Epistemology is the science of knowledge. It's the philosophy of knowledge. So epistemically connected means knowledge connections, right? And the point is that science, in comparison to other areas, is much more epistemically connected. You have much more many applications, and that, for instance, for the engineering sciences, which is probably interesting for some of you, there you find that very regularly. You find it also in other areas, political journalism or contemporary history. There you find it. You may know that or may not know it. If you look at history stuff, it's always many footnotes. And the footnotes means connections to something, right? In the footnotes you say, oh, this is similar than this author said in that book, and here's a parallel case to this one, and so on and so forth. So footnotes usually connect something. Also in your master's thesis, the footnotes connect typically when you cite something or so. Citations is a sort of connection. And what you find in science when you come to this area, which is notoriously difficult to distinguish between engineering science and product development, then the difference, as this is what systematicity theory claims, is a difference in epistemic connectedness. So don't worry about that too much. That is here in one sentence. The scientific domain has a higher degree of epistemic connectedness than the applied domain. And of course, epistemic connectedness is something systematic, right? You put scientific knowledge is all connected with other parts of scientific knowledge, and that, of course, puts it into a systematic, structure of science. Our everyday knowledge is very fragmented. What you know about Hannover, for instance, or where the Mensa is, or things like that, is fairly disconnected from other things what you know about other parts of the earth. It's just very disconnected. But what geographers know about Hannover, they also deal with Hannover, geographers, the science of geography, is then well connected because they may have a theory of cities. of middle-sized cities like Hanover in Western Europe, for instance. They connected, of course, then with that knowledge, whereas our everyday knowledge is disconnected there. We have similar, simple things, where the crepe key is, what how the subway system works, and so on and so forth, but it's fairly disconnected with other stuff, whereas it's one of these characteristic features of science that the different pieces of scientific knowledge are very connected among each other. And you can use that property to distinguish engineering science knowledge from engineering application knowledge, right? So, and you'll see that when you're, for the engineers now, what you learn from the university, at the university in engineering is, of course, always knowledge that has a high degree of epistemic connectedness because you can apply it in many cases. Therefore, you learn it at the university. That is the training you need then later to apply to particular situations which you cannot predict yet, right? You don't know what the job will be, but you have to learn something that's applicable to many situations. And applicability to many situations is just epistemic connectedness. All right. So let's go to the next three. We are running slowly out of time. We've got three more. There in science, there is something extremely interesting. First of all, an observation, which is intercultural, if you wish, observation, namely that the strong and steady increase of knowledge, of scientific knowledge, that is one of the principal differences between science and other kinds of knowledge. If you look at other cultures, some of you may still have a look at their home culture, so-called traditional societies that produce traditional knowledge. I mean, it's all decreasing all over the world, but you may have perhaps from your grandparents still have an idea of what the past in your home country was. And one of the characteristic features of the Western society is that it's regarding its knowledge, especially for the last 400 years, extremely dynamic. It's this increase of knowledge. I mean, this is why you are here. I mean, because you want to participate in this increase of knowledge, and it's an amazingly dynamic process, and it's in world history, it's really unique. Whether it's good or bad is a different story, but this is certainly an observation one has to make. And the question then is, how come? I mean, why is it that scientific knowledge seems to have this drive inbuilt that people work on it to increase it all the time? How come? Well, here is a sort of explanation, at least one motivation. It's not the whole story, but it's part of the story. There is an ideal of completeness with respect to the domain in question in science. There is an ideal of getting to know everything about something, right? Compare that, again, with your knowledge of Hanover. When you try to know something about Hanover, you usually just ask the questions that you need for what you want to do. So you came here, and very early you will have asked, where's the Mensa, right? And where is it where I can sleep, and where I can shop, and blah, 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 and where can I meet people, and so on. So you get your knowledge very punctually according to your needs. And it's very punctual, it's very disconnected, typically. But if you compare that with what geographers now do, for instance, then they want to know everything about Hanover, right? They're not satisfied just to know where this Mensa is. That's not important. They want to know where all the restaurants is. For instance, someone who does a study of cities, geographer, and wants to know what is the distribution of restaurants, for instance, in relationship to different parts of the city, socioeconomic factors, or what else, or what is the distribution of ethnic restaurants, how two cities differ, and so on and so forth. They want to know everything, right? Then about restaurants and the city. So whenever you do science, then of course there is a drive to complete knowledge, and you want to round it up by knowing everything about a certain area, and that of course produces this sort of dynamics. You can look at it now more systematically here. If you look at axiomatic systems, well, you don't know much about that. That's in mathematics. They must be complete. Forget it. The periodic system of elements. I mean, this is an example every one of you is familiar. Of course all the elements must be in there. I mean, that's the whole damn idea of it, right? Of course you want to have all the elements. If you look at physics, you want to have all the fundamental interactions. Here again, for the biologists among you, the classification of biological species, of course it has to be complete, right? You don't want to leave out species. That's the idea of a classification, right? If you have historical processes, then of course the division into periods must be complete. If you have in the humanities editions of certain works, they must be complete. and so on and so forth. We have in science some drive for completeness, and that's of course also an aspect of systematicity, because therefore it's becoming systematic, namely complete. All right, so that's another aspect, and the next aspect is also related here to this completeness, namely that the realization of the ideal of completeness is not pursued at random, but is also pursued systematically, namely knowledge generation. So there are many ways in which, in the sciences, extremely different ways, knowledge is generated, but the knowledge generation, again, the same claim, is more systematic than in other areas, right? So, for instance, the systematic search for new or improved data in archives, measurements, observations, etc. I guess this is something some of you do in your master's thesis, right? You search for new data, improved data, and have, of course, a systematic procedure. You must know if you do something on plants, you must have a priori considerations. How many plants do I have to observe, right? Is it 12 enough, or do I need 500? Can I manage 500, or how many do I need, right? This is something of that sort. Then we have also a procedure very abstractly described here, namely that the sciences have a systematic closing of knowledge gaps. You identify where you don't know something, and you close these gaps on the basis of existing knowledge. Right? You look at what you know already, and you use that knowledge in order to close the knowledge gap, in order to find out what you don't know. That is, of course, why you have the scientific education. Because in the scientific education, you learn something about the field, and what you learn then you use in order to solve a certain problem. That's exactly what you do in your master's thesis. And you need the education for that, right? It's not enough that someone tells you, yeah, just solve the problem. Well, you don't know what to do. So you need to know what's known in the field. So science could be described in chemical terms as an autocatalytic process. You know, autocatalysis is, well, you know in chemistry that a catalytic agent is something that improves a certain reaction. And autocatalyticity is when the system itself is the catalytic agent. And that is how you can describe science. Or for the electrical engineers, a self-amplifying process. There is a systematic exploitation of other domains of knowledge, especially technology. Just think back, well, imagine that 50 years ago, or say, yeah, it started in the 40s, that 60 years ago, 70 years ago, people didn't use computers because there weren't any computers, right, in science. And now everyone uses computers. But if you look at, say, plant biotechnology, I mean, this has nothing, in principle, nothing to do with computers, because it's about plants, it's not about computers, right? But you're using computers. Why? Well, because systematically you see, okay, if I use a computer, I can make calculations I couldn't do otherwise, and then you use them, right? So this is what science does. It systematically exploits everything it can get its hand on that's useful for generating knowledge. And the computer is just one example among many. Just look at all the physical measuring devices that you're using in the life sciences. They come really from physics. All the spectroscopy comes straight from physics, has nothing to do with plants or animals. Spectroscopy is purely physical stuff. And of course, all the chemists and all the biochemists use spectroscopy wherever you can use it. It's a useful device. So exploit in science, you look at the neighboring disciplines, whatever you can use, and systematically gain resources, which is again something which is, of course, somehow used in everyday life. You want to take the train to Göttingen. Yeah, you don't know when the train leaves. Well, you go to the computer and look up in the list of the Deutsche Bundesbahn, when does it leave? You use a technology in order to gain the knowledge. You do that. But you don't do it systematically. You don't look around every day, what new technology could I use in order to get new knowledge about Hanover? You don't do that. You simply say, oh, I want to go to this place, to the library XYZ. I don't know where it is. And then you say, oh, what technology can I use to find it out? Do I use a map? Or do I go to a computer? Or perhaps I simply ask someone, right? Where's the damn library, right? So we do that also, use other stuff. But the difference, again, you see is the systematicity, which is there in play in science, that systematically all these other areas are exploited in order to gain knowledge, all right? There's also something interesting, the systematic exploitation of chance. This is something which probably does not happen in your master's thesis, at least I hope so, because there are brute force approaches. If you look at pharmacology, the development of new drugs, then a large part of this pharmaceutical research is done by brute force approach, and that means you simply try out every possibility, right? You start with a certain substance, and then you change the substance little by little, chemically, you change just a little, and then you run tests on the substance, whether it has potentially biological effects. And you do that, and the number of experiments go in the 100,000s, right? You just have a certain substance, you think, that could be a pharmaceutical of some sort, you don't know anything about it, and then you start using it and modifying it, and then run tests on it, and you do that in very, 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 very long experimental series, 100,000s of runs there with these substances. And this is, of course, you don't know what's happening, but by chance it could happen. That's one of these particular then compounds is pharmaceutically useful, and you run on them by doing this brute force approach, and that means you don't rely on chance, that by chance someone will discover that one day, but you simply force chance, right, by systematic exploitation of chance, so to speak. That's a brute force approaches, explorative experimentation, and also chance discoveries during tests of hypotheses belong to this area. And then, of course, it's again, if you compare it with our everyday practices, I mean, yes, by chance you may hear something that's interesting to you, but we never do that in that systematic way that the sciences do it. So again, you see this aspect of systematicity. And finally, and again, this is pretty obvious from anyone who uses any science, that the structure of and representation of knowledge in science is extremely systematic, much, much more systematic than anything we do in everyday life. So in the formal sciences, you have the axiomatic representation. Again, it's not so interesting to you. If you look at the non-formal sciences, then there are certain distinctions. Again, I don't go into details for time reasons, but here is something really fascinating. It's the special forms of representation that science has developed in different areas. The nomenclature. Just imagine when I told you in the description section that in organic chemistry we're talking something like 10 million compounds. You must have names for them, right? You must, if you want to talk about one of these compounds, you must be able to have a name for them. So you need a naming system that distinguishes unambiguously 10 million different items. And that is the nomenclature that has been developed in organic chemistry. Right? The same holds, of course, in biology, where you have also something like 10 million items you have to distinguish. Holds also for geography. There are geographical systems about the United States that feature something like 5 million different items. You have to have a naming system. And you have, of course, if you look at the sciences, different areas, you have, of course, nomenclature is only one thing, a system of names. You have graphs and maps and tables and catalogs and whatnot. Right? If you go to the internet and then Google representation in science, it's amazing what's there. And of course, we have also language and use pictures and whatnot in everyday life and so on. But of course, given this wealth of data that has to be described and named in the sciences, it's not amazing that also in that respect, namely structure and representation of knowledge, the sciences are immensely more systematic than anything else. Right? So again, in this dimension, you see the main thesis. Here's a final remark, right in time, that the systematic representation also increases, well, the efficiency of knowledge perception. If you know your nomenclature, then you can quicker read and understand what's going on. It also supports error elimination. If you have systematic development, as in a textbook of the science that you are dealing with, then you see more easily where errors are and also where gaps are, where it's something which you don't understand yet, because you see, oh yeah, I understand that, oh, here's a gap, here's something missing. So what you have here, and this is the main story, that you have a positive feedback between different aspects of systematicity. So when you are in these 9 dimensions, when you are very systematic, say in dimension 9, it also helps you for dimension 4. right? And for dimension 7, for instance, right? So it's so that these different aspects of systematicity are themselves in a net of relationships, and they support each other. So the general picture that you're getting then from systematicity theory is that there are many aspects of systematicity also even correlated, and that science as a whole is then a very complicated network of different forms of systematicity in the different dimensions, and that the whole system is built to increase its systematicity in all the dimensions that are possible, right? Better explanations, more systematic explanations, more systematic descriptions, completeness, increase the closing of knowledge gap, eliminate error systematically, and so on and so forth. So this is the picture you get from systematicity theory. It seems to be a picture that has certainly quite some plausibility and some advantages. If you want to read something about systematicity, here's an article that you can download in an Israeli journal. I hope you don't mind it's an Israeli journal. I would also publish in a Syrian journal or in an African journal if I get the offer to do so. Because I'm saying that because once a student came to me, oh, you're publishing in an Israeli journal, I don't like Israel. Fine with me. I would also publish in a Syrian or whatever country, Palestinian, whatever. I don't care. So here you can read something about it, but for the purpose of what we do next, you don't need that. All right? So now the part of my long speeches has ended here, and I'm looking forward to the talks that I get from you next time. Have fun in the meantime, and I look forward to that. See you then.